Okay, we're going to continue on talking about some more details about the hyperbolas and ellipses, kind of assembling them both together into one concept. I want to first remind you about the important parts of the ellipse definition. First of all, the locus. That means the set of all points that would fit this description, where the sum, the total of the distances from any point on the ellipse to the focus points remains constant. And you've seen an animation of that. You saw the two focus points and then the string tied between them. The hyperbola follows this definition. Again, it's the locus of points, the set of all points, such that the difference, meaning the subtraction between the two distances to the foci, remain constant. So, for instance, if I picked this point right here, I'll call it P1, and I measure from P1 to F1 and from P1 to F2, that if I took those two distances, I would get some constant. In fact, I'll put it in the absolute value because I could pick a different point, say P sub 2, and measure those same two distances. And you can see they're going to be different distances, but, oops, that was supposed to be P1. That those are going to remain the same. Now, I did find this animation that perhaps will be slightly instructive. You'll notice first that here are the two focus points, 1 and 2, and they've got this string hooked from this focus point tagged to the end of this ruler. And you'll notice the other end of the ruler is hooked to the other focus point. And so as we move this thing, and you'll notice that the pencil stays firmly stuck up against the edge of the ruler. And there's just no way that I could do this by hand, but you can see that you get this kind of nice sort of hyperbolic sort of thing. And if you look over here on the right side, and I'll just hide the left, you can see the exact same thing, except they've got it niftily animated so that schlup like me doesn't have to actually run the slider. But that's the way it would work. That's the way the ellipse is defined. And the concept is that any given point here, if I take this total plus this total, it's gonna, subtract the two, you get the same distance. So anyways, I don't know if that helps at all envision it, but you're certainly welcome to look at that again. Alright, so let's get back to the notes here. And here's a sample type of problem that you might see on the homework where they describe this hyperbola in this manner. So I'm going to kind of quickly go through this. In fact, I'm going to pause the recording while I set these graphs up. Okay, so picking up here, you see I've got this graph started with some two focus points plotted that I was given. I sketched these 2 points. That part was easy. Clearly the center has to be halfway between those two. So as I consider from positive 3 to negative 7, that's 10. So the distance from the focus to there must be 5. So the center should be at 4 comma negative 2. And you can see that that's 5 units this direction and 5 units this direction. Now that should also be the letter C, because perhaps you'll recall that the letter C for both the hyperbola and the ellipse, that's the distance. Now, it doesn't have to be the letter C, but that's what everybody uses for it. So the distance from the center to a focus point is C. Alright, so I've got C is equal to 5. Now, we go down here to the star, where it's added some information. It adds this fact that the transverse axis, remember that's the main axis, or actually, maybe a more accurate way to put it is the direction the hyperbola travels in, has a length of 8. Okay, so since the focus points are up and down, that must mean the hyperbola is going up and down. And so since the transverse axis has a length of 8, that means that A equals 4. So I'm going to use blue for this. So I'm going to go up 4, That's a vertex point, and down 4. So my two vertex points are at 4, -6, and 4, +2. Okay, and that's actually the edge of my rectangle of some sort. I've got to figure out what the rest of it is, though. So I've got to find the equation and a complete graph. So here's the thing. I know A, and I know C, and I know because in a hyperbola that the C has to be bigger than A or B, because the distance to the focus has to be outside that, then I know it has to fit this description. C squared equals A squared plus B squared. So C was equal to 5, and A was 4, and B we don't know. Do a little bit of math magic. I guess you'll just have to trust me that it's going to be 3. So that tells me that if I count out 3 units this way, oops, and 3 units the other direction, so right there, those would be my other vertex points. I would get my asymptotes going straight through the corners. Close enough. And the conic section sweeps up like that. Okay, it should not hit the asymptotes, but it's close enough. Alright, so that's my graph. I don't have the LR listed yet, but I'll get to that in just a second. But I want to find the equation next. Since this thing is going up and down, I know it's going to be y plus or minus something. And since it's a hyperbola, I know that it's a subtraction sign in there. And I know it's equal to 1. Since it was going up and down a distance of 4 units from the center, then this must be 4 squared. And since it was going left and right 3 units, that must be 3 squared. The center was at 4, -2. That should be the equation right there. The last thing I want to do is find the lattice rectum, which is 2b squared over a. So in this case, it would be 2 times 9 over 4, 18 over 4. That would be something like 4.5, the length of the LR. And that would be this segment that goes right through that focus point. Oh, nuts. Goes right through that focus point, and it should be 4.5 units long. Okay, I'm going to pause here while I collect my wits to find the equation of the asymptotes. Oh yeah, so I need the center, x minus 4 and y minus a -2, so it's actually y plus 2. And my slope from the center line is going up 4 to the right 3, so this must be 4/3. So I'm good to go. Alright, I'm going to pause again here, and we're going to talk next about the concepts that are common to ellipses and hyperbolas. Okay, as I mentioned already, the concept of the lattice rectum is something that's common to both the ellipse and the hyperbola, both of them, and they both have this exact same formula. Since we've talked about that already, I'm not going to continue to belabor that point, but I do need to talk to you about this guy right here, the eccentricity, which is in math terms, it's a measure of the roundness of the conic section, and it always falls under this definition, that the eccentricity is equal to the distance, it's a ratio, the distance from the center to the vertex, the center to the focus, that's the letter C, divided by the major axis length, or in this case the semi-major axis length, or the transverse axis length. Alright, so I'm going to pull up a little demo here to try to illustrate. Okay, here's the demo. You'll notice that I've got this slider right here, where the eccentricity is 1.56. Alright, and so the red line is what we get when the eccentricity is 1.56. And you'll notice as I pull this back and forth, you can see the red lines changing because that's a hyperbola. Okay, so when the eccentricity is 2.28, we get this kind of hyperbola shape. And you'll notice that as I get closer and closer to 1, it's a little hard to see, but you can see down here this it's still a hyperbola, but notice how much closer this hyperbola is starting to match this parabola looking thing. In fact, the closer we get to 1, where the ratio between those two are the same, you can see how far away the other part of the hyperbola has gotten, way down there. Okay, the closer we get to 1, the closer this thing is to a parabola. In fact, when you get to exactly 1, the red line has disappeared. It's laying right on top of the gray line, and the other part of the hyperbola is completely gone. It's not there anymore. Now, as soon as we switch past 1 and we get to 0.9 or 0.8, now this is kind of hard to see, but it's actually an ellipse. It doesn't draw it all the way because that's the nature of this program, but you can see that as soon as it's getting past below 1, then it's more of an ellipse, and the closer it's getting to 0, the more round it's getting, the rounder it's getting, the more like a circle it gets. So the closer it is to 0, the more like a circle. The closer it is to 1, the more like a parabola. When it equals 1, it is a parabola. When it gets greater than 1 and beyond, it's a hyperbola. Alright, let's go back to our notes here, and let's fill in a few things here. When the eccentricity is 1, we get a parabola. In this range, we get an ellipse. I'm going to stick with math, keep away from English. Right here at 0, for my eccentricity, I get a circle. And when the eccentricity is greater than 1 and beyond, I get a hyperbola. Okay? So, those are the important parts about the ellipse. Okay, so from here on out, every graph needs to include the length of the lattice rectum. I said the length of the lattice rectum. It's going to have to find the eccentricities and the endpoints on the two axes, the coordinates, the foci, the center, etc. You find everything. All right, and that's where I'm going to stop right now.